Chapter 8.3.3 Particles and Forces. By the end of this section, you should be able to define baryons, mesons and photons in the standard model. Previously, we saw what the standard model was. Explain why high energies are required to investigate fundamental particles. So, I think I showed you the classification for baryons and mesons. All of them are classified under hadrons. So here, if you go back to the notes here, we have families of particles, and then we have hadrons and leptons. Now under hadrons, you have baryons and mesons. Baryons are made up of 3 quarks. Mesons are made up of a quark and an antiquark. Examples of baryons are neutron and proton. Examples of mesons are pi plus meson, which is made up of up quark, and an antiquark, which is the anti-down quark here you see. And then phi meson is made up of a strange quark and an anti-strange quark. So baryons and mesons are classified under hadrons. They are all hadrons. All of these are made up of quarks or quarks and an antiquark. So let's go back to the lesson. Explain why. Okay, so baryons, if 3 quarks are combined together, the resulting particle is a baryon. Figure A. You can see several examples here. Proton is a baryon, neutron is a baryon. Proton is made up of 2 up quarks and 1 down quark. You should know this. Neutron is made up of 1 up quark and 2 down quarks. Again, you should know this. 3 quark baryons. 3 antiquarks in the antiproton make it an antibaryon. So you can see here antiproton. You can see here proton. Here you have antiproton. Anti-up quark, anti-up quark, anti-down quark. Here you have all quarks, no antiquarks. Up quark, down quark. Here anti-up quark, anti-up quark, anti-down quark. So all of these quarks you have in the antiproton, all are antiparticles of the quarks here. 3 quark baryons, 3 antiquarks in the antiproton make it an antibaryon. So this is an antibaryon. And here you have lambda 0. So lambda 0. You can try to find out what the total charge here is. You remember previously we learned that up quark is plus 2 over 3. Strange quark is minus 1 over 3. Down quark is also minus 1 over 3. So if you add all these together, 2 over 3 minus 1 over 3 minus 1 over 3 is 0. So from the name itself you can figure out that the charge here is 0. Okay, if you go back to the notes here, you can see, yeah, even here see pi plus meson. So I explained in the previous video lesson that when you total the charge here, it will be a plus 1. Here when you total the charge, it will be 0. You should know how to get the charge based on the charges of the fundamental particles, that is the charges of the quarks. You should know this because in the exam paper they can ask you to find the charge of that particle. Okay, protons and neutrons are baryons. A proton consists of 2 up quarks and a down quark, whilst a neutron is 2 down quarks combined with an up quark. Other baryons are more obscure and have very short lives as they decay through a strong nuclear force reaction that makes them highly unstable. Previously we learned that the strong nuclear force acts on quarks. They do not act on leptons. And also we came across the weak interaction, also called the weak nuclear force, which acts on both quarks and leptons. See, this note is important. Other baryons are more obscure. Okay, we went through that. Yeah. Yet other baryons like the sigma, omega and lambda particles decay via the weak nuclear force and are longer lived. Now remember, the weak nuclear force acts on both quarks as well as on leptons, but strong nuclear force doesn't act on leptons. Yet other baryons like the sigma, omega and lambda particles decay via the weak nuclear force. Weak nuclear force is also called the weak interaction, with lives as long as 10 to the power minus 10 seconds. It's a very short time. Okay, so that is about baryons. Now let's see mesons. Again, if you look at the notes here, mesons are made up of a quark and an antiquark. These are examples of mesons. Now here also you have examples of mesons. See, pi plus meson, what we saw in the notes here. Pi plus meson is made up of up quark and an anti-down quark. See, up quark and an anti-down quark. And let's check whether this is the phi meson. phi meson, but that is no, that's not there, right? Yeah, phi 0 is there. Phi, yes, okay. No, this is phi. This is something else. This is phi, right? Phi is another Greek letter. Pi is one Greek letter. Phi is another Greek letter. Yeah, this I think is the Greek letter phi. Okay, anyway, we'll see. If a quark and an antiquark are combined together, the resulting particle is known as a meson. Meson. The Pion and the Kaon are the most common examples of mesons. So Kaon, Pion, so you can see. Yeah, pi plus meson, U up quark and anti down quark, you can see that here, we saw that in the notes also, is made up of an up quark combined with an anti down quark. If a meson is a combination of a quark and its anti-quark, then the meson's charge must be 0. So you saw that over here. See, it's the quark and the anti-quark of that quark. So anti-quark means the charge will be opposite. So here the total charge is 0. That's what they mean by this sentence. If a meson is a combination of a quark and its antiquark, then the meson's charge must be 0. This is the case for J or phi particle, psi particle. Again, these are all Greek letters. I have shown you the Greek alphabet, so we can have a look at what the letter is, because sometimes some of these letters are not used that much, and we use a lot of these Greek letters when it comes to particle physics. So that's why I have shared the Greek alphabet with you, so that you know what these Greek letters are. Alright, you see here, this is the Greek letter psi, psi. Phi is another Greek letter. Okay, yeah, this is phi. See, psi, phi, and this is pi. Different Greek letters are used. So this is the J or psi particle, which was discovered in 1974 by 2 independent researchers at separate laboratories. Its slow decay with a lifetime of 7.2 into 10 to the power minus 21 seconds occurred when it was not traveling at relativistic speeds. So was a genuine and unexpected long lifetime. So was a genuine. This did not fit the pattern generated by up, down and strange quarks, and it is thought to be a charm anti-charm combination. So here the total charge will be of that particle will be 0. The 2 independent discoverers of this, Richter and Ting, shared the 1976 Nobel Prize for their discovery of the 4th quark. Okay, so you can see that here the psi meson, psi. Mesons are formed from quark and antiquark combination. So you can see quark and antiquark. Here it's the quark and its antiquark. Here also the quark and its antiquark. Okay. So Kaon also is the Pion, Kaon. Okay, hadrons. Now I told you what hadrons are. We went through the table earlier. By the way, this is the Greek alphabet. It's better if you know these, both capital and simple letters, because especially for particle physics, we use a lot of Greek letters. That's why I have shared this with you all. Okay, so the hadrons are classified under baryon. Hadrons consist of baryons and mesons. Okay, so let's see. Quarks can interact via the strong nuclear force. Remember the strong nuclear force acts on quarks. It doesn't act on leptons. The weak nuclear force acts on both leptons and quarks. Thus, baryons and mesons can interact via the strong nuclear force. Any particle which feels the strong force is called a hadron. So, baryons and mesons are both hadrons. Leptons do not feel the strong force, and so are in a separate class of particles from the hadrons. You can see I have correctly classified it here. See, families of particles, hadrons and leptons. Quarks and leptons are fundamental particles. Okay, then the 4 forces of the apocalypse. There are 4 other particles that have not yet mentioned here, that we have not yet mentioned here, because they are not matter particles. These are known together as exchange bosons. The matter particles interact by the four forces of nature, which are gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. So you can see the four forces of nature. The matter particles interact by the four forces of nature. So gravitational force, okay, electromagnetic force, strong nuclear force, weak interaction, also called weak nuclear force. Each force acts on particles which have a certain property, such as mass in the case of gravity, or electric charge for electromagnetic force. The process by which these forces act has been modeled by scientists as an exchange of another type of particles, the exchange bosons. Okay, so as an exchange of another type of particle known as, for example, for a proton and an electron to attract each other's opposite charge, they pass photons backwards and forwards between each other. Okay, so you can see something like this. The examination specification for exchange bosons is limited to photons only. So here, but still we can go through this for additional information. Specification means the syllabus. So for the Edexcel students, specification means the syllabus. Okay, gluons in combination with virtual quark and antiquark pairs are exchanged between quarks to hold the quarks together. In this example, the three quarks form a proton. It may sound bizarre, but this has been shown experimentally to be an appropriate model for the electromagnetic strong and weak forces. So this is a hypothesis. So they are telling based on the theory and all, they come up with this. Now the same thing happened, remember in the previous video lesson I told you about the down quark. Over here you can see the bottom quark and the top quark. So before they found this out, they predicted based on the experiments that these quarks should be existing, but they had not found it. So based on their theory, there was a hypothesis that this will be there, and finally they found it. Similarly over here also it is something like that. They say this can be there, so probably in the future they would find it. It may sound bizarre, but this has been shown experimentally to be an appropriate model for the electromagnetic strong and weak forces. In the case of gravity, the so-called graviton has been theoretically invented, you see, has been theoretically invented to complete the model, but gravitons are yet to be discovered. Many experiments have been set up recently to try and detect gravitons. So it's again, like I said, based on what we discussed here. You can see it's linked to this, and based on that they say this particle could be there, and they could discover it. They want to discover it. See, the process by which these forces act has been modeled by as an exchange of another type of particles, the exchange bosons. For example, a proton and electron to attract each other's opposite charge, they pass photons. They pass photons backwards and forwards between each other. So we have the graviton. Okay. Then many experiments have been, okay. So here you can see force, electromagnetic force, weak nuclear force, also called weak interaction, then strong nuclear force, gravity, exchange boson, photon. Now in the case of electromagnetic waves we have this, then weak nuclear W or Z boson, strong nuclear force gluon, gravity graviton, then boson symbol, boson charge, boson mass undetermined. Okay, so here you can see on for the specification, the examination specification for the exchange boson is limited to photons only. So like I said, this like additional information, for additional information you can know this. Whilst gravity is the force we experience most obviously, it is the one scientists know the least details about. It is the one scientists know the least details about. The electromagnetic force is well understood, and the exchange of photons to make it work has also led to an understanding of the generation of photons such as light. The weak nuclear force is also fairly well understood, as the W and Z bosons predicted by theory have since been detected in accelerator experiments in which protons are crashed together. Okay, WOZ boson. See, this is particularly strong science, as the existence of the weak nuclear force bosons had been theoretically predicted, and then they were detected in later experiments. Many particle decays where other particles are formed, such as beta decay, occur via a weak nuclear force interaction. In the notes I have mentioned this. See, weak nuclear force are responsible for beta decay. Okay, so they mentioned that here many particle decays where other particles are formed, such as beta decay, occur via a weak nuclear force interaction. Okay, so we have come to the end of this subchapter, and make sure you answer all these questions and check the answers at the back of the book so that you have a better understanding of what you learned here. You can also go through this part if you think you need more details. And then definitions here are important. Baryon is made up of a combination of 3 quarks. We saw that in the chart also in our notes. Meson is a particle made up of a combination of a quark and an antiquark. That was also there. A pion is a meson created from any combination of up and down quark or antiquark pairings. Up and down quark and antiquark pairings. Because if it's a meson, it is made up of a quark and an antiquark. So pion. Okay, so this is pi plus meson. So this you can see is a quark and an antiquark. So pion is a meson created from any combination of up and down quark antiquark pairings. See, up and down quark antiquark pairings, pion. A kaon is a meson created from any combination of an up or down quark antiquark and a strange or anti-strange quark. So you can see that here. See this one, right? Can you see that? Kaon, down and anti-strange quarks created from a combination of up or down quark and anti-strange and a strange or anti-strange quark. A hadron is a particle which can interact via the strong nuclear force. So baryons, mesons, they are all hadrons. Exchange boson, again this also I have shown you in the chart here for the notes of these particles. Okay, strong nuclear force is the strongest of the 4 fundamental force. Okay, before that here, hadron is a particle which can interact via the strong nuclear force. Exchange bosons are particles that enable the transfer of force. Each of the 4 fundamental forces has its own exchange boson. Now for more details you can see this part. Okay, remember the particles, metaparticles interact by the 4 forces of nature, which are gravity, electromagnetic force, strong nuclear force and the weak nuclear force. Okay, exchange bosons are particles that enable the transfer of force. Each of the 4 fundamental forces has its own exchange boson. Like I said, the details are here. Okay, see, the process by which these forces act has been modeled by scientists as an exchange of another type of particle, the exchange boson. Okay. So here also diagram is given. Gluons is a combination with virtual quark-antiquark. Pairs are exchanged between quarks to hold the quarks together. In this example, the 3 quarks form a proton. Alright, so let's go through this. Gravity is the weakest of the 4 fundamental forces transmitted by the theoretical graviton particle and affecting all objects. Okay, see, graviton affecting all objects. The electromagnetic force is one of the 4 fundamental forces transmitted by photons, acting between objects with charges. Okay, so now you know that also. 4 fundamental. Now again the 4 fundamental, they are all here. 1, 2, 3, 4. So electromagnetic is one of the 4 fundamental forces transmitted by photons, acting between objects with charges. So they have to have charge for this force to act. Electromagnetic force transmitted by photons acting. Okay, the strong nuclear force is the strongest of the 4 fundamental forces transmitted by gluons acting at very short ranges, 10 to the power minus 15 meters between hadrons. Strong nuclear force is the strongest of the four fundamental forces. Now you saw what the four fundamental forces are: electromagnetic, gravity, strong nuclear force, and the weak nuclear force or weak interaction. So out of those four, this is the strongest of the four fundamental forces out of these four. Okay. And remember, it acts at very short distances. Here also I have given 10 to the power somewhere close to -14. In this book they say like -15 meters between hadrons. In that range, 10 to the power -14, 10 to the power -15 meter range. It's the strongest of transmitted by gluons acting at very short ranges between hadrons. The weak nuclear force is one of the four fundamental forces transmitted by W or Z bosons. Okay, so you can see this here also. Acting at extremely short ranges, 10 to the power -18 meters. It can affect all matter particles. It can affect all matter particles. Photons are the quantum of electromagnetic radiation and force carrier for the electromagnetic force. Okay, so you can see a graviton is the force carrier particle or exchange boson. See, force carrier particle or exchange boson for gravity. Alright, so we have come to the end of this lesson. Make sure you answer all these questions and check the answers at the back of the book. If you feel like you need more information on this, go through this part again about the bosons and all. Now this exchange boson is graviton is the force carrier particle or exchange boson for gravity. So for more details you can go through that, and I think you will have a better understanding. Next we will see particle reactions like beta minus decay, beta plus decay, alpha decay. Okay, what happens there, and also you can see the particles here. Remember the 6 leptons, and then various particles and antiparticle and their properties. You can see here the different letters being used. That's why I told you even the Greek letters are important, because we can use them for these particles. Alright, so we will end that here. Next we will see chapter 8.3 part 4 or chapter 8.3.4 particle reactions.